book, or actually in this class, we're not required to cover section 3.3. It's an optional section. So I, as a teacher, always make the executive decision not to cover it now because we never know how much time we'll have in the future. So I'd rather have enough time to spend on all the mandatory sections. And if for some reason we have extra time, we can come back to it. I typically don't, just because you'll kind of see enough of it in the future anyway. It's not that big of a deal. So 3.4 is still going along with what we've learned. Measuring the middle, measuring the spread. Now we're measuring position. So when we did 3.2, measuring the spread, it was kind of position, but it was all like related to the mean. And 3.4 just means where do I lie compared to everybody else, all right? So it's different ways to interpret where you lie compared to the rest of the data. So the first section is called Z-scores, determine and interpret Z-scores. Z-scores, guys, are a concept that you guys do. You do it awesome on the test, and then you completely forget about it, which is okay, because I was that type of student too. But coming back in Chapter 7, guess who's coming back? Z-scores, all right? And I'll remind you again in Chapter 7 when we get there. What are Z-scores? They represent the distance that a data value is from the mean, but in terms of the number of standard deviations. So instead of saying I'm 8 points away from the mean, I could say I'm 2 standard deviations away from the mean. So I'd have a Z-score of 2. How do you get it? You obtain it by subtracting the mean from the data value, so that's your distance from the mean, but then you divide by the standard deviation to see what it is in terms of standard deviation. So here's a handful of examples, and I know we're just kind of jumping right into it, so if it's not quite making sense right now, that's okay. Say this is the average age of the students in our class. Say on average the mean is 20 years old, and the standard deviation is 6 years old. If you were 26, what would your Z-score be? Well, would you guys agree that's a gap of 6 years, right? But how does 6 years compare to the standard deviation of 6? It matches exactly at once, right? So since you're exactly a difference of 6, which was the standard deviation, you have a Z-score of 1, meaning you're 1 standard deviation higher than the mean. Say for some reason you're 14 and you're in this class. Again, do you guys agree that gap is 6? But it would be a -6 because you're 6 years younger. So you're a full standard deviation lower than the mean, so that's why it's negative. 17, that's a gap of 3. But how does 3 relate to your standard deviation of 6? It's a half of it. So you're a half of a standard deviation lower. That's why it's negative. And if you were 20 exactly, you are exactly the mean. So your Z-score would be 0 because you're 0 units away from your mean, okay? Notice the formulas are like, oh, great. Look at all these new formulas that I have to memorize. 1, you don't have to memorize them. And 2, they actually are the exact same formula. They're just using different symbols because one's for population and one's for sample. So what does mu always stand for? Your population mean. And what does sigma always stand for? Well, you just learned it. It's your population standard deviation. And guys, anytime you have a normal x, that's just your individual data value. So what you're going to do is you're going to take your individual data value minus the population mean and divide by the population standard deviation. And that will give you your Z-score. Over here, if you look to the right, it's the exact same idea, but since it's for a sample, you have x bar, which is your sample mean, and you have S, which is your sample standard deviation. So really when you get down to it, just always remember, take your number minus the mean, whether it's a population or a sample, it doesn't matter, and divide by the standard deviation. Okay? So have you guys heard of the term, you can't compare apples to oranges? Are you too young for that? Just basically apples and oranges are completely different fruits, so you can't really compare them. That same goes with your classes you're taking. Like you can't compare stats to your human anatomy to your music class, right? They're all different. So say you're in a class, or 3 classes, stats, biology, and kayaking, and you have a test that same day for all 3. How do you compare in general in each of your classes? The best score is not always the best score because your classes differ in difficulty, okay? So whenever you have to compare different situations, this is when you're going to use Z-scores, all right? So Pat received a grade of 82 on her stats exam, where the mean grade was 74 and the standard deviation was 12. So let's write a mu over 74 because that was the mean. and a sigma by 12 because that was a standard deviation. What Pat gets is that individual data value, that is X. All right? So let's do this for her stats class. Let's figure out what her z-score is. X minus mu over sigma. All right? How did she do? She got an 82. How did the rest of the class do? They got a 74 with a standard deviation. That's a pretty big standard deviation. So that's a pretty big spread, meaning the students either did really, really well or really, really bad, so there's a big spread of their data. The number one thing I want to point out, and I'll say it, and I know you guys know, but order of operations, you cannot just type this in the calculator as is without putting parentheses, right? If you do, it'll just take 74 divided by 12, not the gap. And so I just do the top first, get an answer, and then divide by 12. So I always just do this. What's the gap? 8 over 12, and then I put that in your calculator, okay? You round z-scores to 2 decimals, and you'll see in Chapter 7 why, okay? So this one, I believe, is 0.6 repeating, so that's going to be a z-score of 0.67. Guys, 8 over 12 reduces to, what is that, 2/3? So basically, she scored 2/3 of a standard deviation higher. If she scored completely 12 points higher, she would be a full standard deviation over, but 8 was not quite 12, so she's not quite a whole standard deviation higher. Do the same thing for bio. Let's see what's going on there. Pat received a grade of 72 on her biology exam, where the mean grade, so we're going to label that mu, was 65, and the standard deviation was 10, so that's going to be sigma. So basically, we want to know, in general, like 72 is not as good as an 82, right? But notice the mean here was a 65, and this mean was a 74. So she may have done better in bio relative to the rest of the class. So you have z equals x minus mu over sigma. You take her grade of a 72 minus the mean grade of 65 all over the standard deviation of 10. And again, the gap, she scored 7 points higher, which was not quite a full standard deviation. So she gets 0.7 or a z-score of 0.70. And notice what happened there. That's more than 2/3 higher. That's 0.7. So far, relative to the rest of the class, she actually did better in bio than stats because must have been a harder test. Last but not least, we have a kayaking exam. Do you guys know that we have a walking class on campus? We don't have a kayaking class, but we have a walking class. So if you ever are short of a couple credits and you need to have a full load, sign up for the walking class. I would like to think that's an easy A and you're getting fit at the same time. What happened here in this kayaking class, guys? She got a 91. Awesome. But I'm sure everybody else did just as well, right? So look at the mean grade was an 88, so that's our mu, and the standard deviation was a 6, so that's our sigma. So even though she got a 91, everybody else fared just as well. Okay, so we have x minus mu over sigma equals 91 her grade minus the 88 over the 6. And that is a spread of 3 over 6 or 0.5. Does that look right, guys? All right. So in my math lab, I think a couple of them, they'll ask you what the actual z-score is. But some of them, you're just answering this question. In which class did she receive the highest relative grade? Biology. And that's what all they're looking for. So you might be off on the side doing the z-score like on your calculator or something, but they don't even care what it is. They just care that you know that you're finding your z-score and that's what it is. She did best in biology. So just because her grade was not the highest, 72 was actually the lowest exam score that she received, but obviously it was a harder test because in relative to the rest of the class, she scored a lot better. Is that okay? So that just lets you know position. How high am I compared to the rest of the class? Another way to measure position is percentiles. Since percentiles can be generic, they represent it with K. So like the 5th percentile, the 10th percentile, whatever it may be, is denoted P sub K. Of a set of data is the value such that K% of the observations are less than or equal to the value. What does that mean? I don't know if you guys remember going to the doctor's office and they put you like on a growth chart. Like I was always a giant, so I was always like 95th in height. Do you guys know what I'm talking about? Like percent, or those that are going to nursing, you're gonna have to deal with those. So it just lets you know that percent and lower are shorter than you. So like my daughter Hazel, she's 5, she's a beanpole, so she's like always 95th in height and 40th in weight. So she's taller than 95% of all other 5-year-olds, but only weighs more than 40% of all other 5-year-olds, okay? So the key thing is it's always kind of shading to the left. I don't know if you want to draw a picture. We can do a bell curve. And it's always shading to the left, okay? Percentiles are always going that direction. But it's kind of like what we did earlier with the empirical rule. If she's 95th percentile in height, that means she's taller than 95% of 5-year-olds, but what percent's taller than her? 5%, okay? So you can still kind of do that complement rule. Guys, that's all the more you're going to have to do with it, okay? You're just going to have to know that that percent is lower, and the complement, what would add up to 100, is higher, all right? So let's see what's going on with this example. So Mary just received an exit exam score of 78% for the nursing program, which scored her in the 86th percentile. What does this mean? First of all, do you guys realize that this is not needed? Just because she got a 78 has nothing to do with the problem. What we care about is that she was in the 86th percentile. By giving us that percentile, they've given us 2 bits of information. We know what percent she scored better than, and we know what percent scored better than her. Okay? What percent did she score better than? 86, right? So Mary scored, we'll do 2 bullets. Mary scored better than 86% of other testers, I guess we can call them, right? So, I mean, I guess you could play around with the 78%. 86% of other testers scored a 78 or lower, right? And then what do we know? What percent scored higher than her? 14. 14% of testers scored higher than Mary. So again, you could say, okay, we know at least 14% scored a 78% or better. That's all you have to do. In the older version of the book, guys, you had to like calculate percentiles based on your data, and it got really complicated. Percent literally means per 100. So that's why 100% is our deviations, and each percent can be met. Is that okay? All right. So quartiles are something kind of new, but the root in quartile is quart, right? Meaning force. So we're basically, instead of doing it percent per 100, we're dividing things into quarters. So like, are you in the first quarter, second quarter, third quarter, or fourth quarter? Kind of reminds me of school, right? So quartiles divide the data sets into fourths or 4 equal parts. The first quartile is denoted Q1, and that divides the bottom 25% of the data from the top 75%. But note that the first quartile is therefore the same as the 25th percentile, right? So Q1, the first, think of quarters. If you have a quarter, you have 25%, right? The second quartile is denoted Q2. It's equivalent to the 50th percentile. It's also the median, guys. Your Q2 is also the median because it just divides your data in half, right? 50% is below it, 50% is above it. And last but not least, the third quartile is your bottom 75% with your top 25, aka the 75th percentile. So these break it down by percents, like single percents, or these just break it down by quarters. I'm going to do this one time with you by hand. Never again do it by hand, okay? So we'll write use a calculator. It is not bad to do by hand at all. It really isn't. But if we're throwing this crap in our calculator anyway to figure out standard deviation or whatever it may be, that we might as well get this, okay? So the first thing is to make sure your data is arranged in ascending order. So remember with median, it said ascending order, and I said it didn't really matter. With median, it could go high to low or low to high. But with quartiles, it does matter. So that's why I think they try to stay consistent, and it's always ascending, okay? The first thing we're going to actually concentrate on is finding the median, or Q2. So we're going to try to find Q2 first, which is just the median. Well, how many data values do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. So how are we going to get the median of 14 data values? Average which 2 numbers?
16 and 19.
Right, the 7th and the 8th, right? So we're going to go 1, 2, 3, 4, 5, 6, 7. So our median, guys, is right here. Okay, so we're going to average 16 and 19 by adding them and dividing by 2. You put that in your calculator, beeper, bopper, beep, you get 35 over 2, or 17.5 units, whatever this is representing. And basically from there, we're just going to keep cutting in half, right? Like if I give you a cookie cake and I ask you to cut it into fourths, do you try to cut a quarter? No, you'll cut it in half and then cut it in half again. And that's all we're doing, all right? So now we have 1, 2, 3, 4, 5, 6, 7 data values. The middle of these data values will be your Q1, your first quartile, okay? What's the middle of those 7 data values? 7. So that will just be 7. And then you do the same thing to get Q3, okay? You just ignore the bottom half and cut the upper half in half. 1, 2, 3, 4, 5, 6, 7. So 27 is your Q3. Do you guys see how I did that? You cut it in half first, and then you cut each of those halves in half. If it just so happens that when you cut it in half, there's an even amount of data here, just do the same thing we had to do with Q2, right? You would average your middle 2 values of the bottom half to get your Q1. You would average the middle 2 values to get your Q3. Get your calculator out. I want to show you how easy it is to put in your calculator. So this is a good review. What we're going to do is we're going to write this data into our list 1. If you're in the middle of a problem and you don't want to put it in your list 1, you want to put it in list 2, that's fine. So you go to Stat, Edit, Enter. I have data in list 1 that I don't want there, so I'm going to go highlight list 1 and hit Clear, Enter to clear it all out. And then one by one, I'm going to put my data set, okay? 1, 3, 4. Remember, this will be the most time-consuming part, so take your time and make sure all the data values are entered in correctly. Okay? Once you have your data in correctly, basically chapter 3, guys, the one thing, well, there's 2. There's that random generator, but this will get you through all of chapter 3, okay? You hit Stat, you scroll over to Calculate, and you hit One Variable Stats. If you have a newer calculator, tell it which list you want it to go to. If you have an older one and it's on list 1, it automatically defaults to list 1, and you hit Enter. On the test, I don't want you to have to enter data in over and over and over again, because the more time you have to enter data, the more chance there is for you to mess it up. So honestly, in chapter 3, I only give you 1, maybe 2 data sets, okay? So with the same data set, I might ask you for the mean, standard deviation, variance, range, all that stuff that we learned in chapter 3, okay? So notice the means here, sample standard deviation is S, sigma is 11, but what we care about is the quartiles. This arrow means you arrow down. Look what you have. You have a Q1 of 7. It's not what we said Q1 was. You have a median, which is Q2 of 17.5. That's what we said it was. And a Q3 of 27. These have units as well. This doesn't really have a word problem with it, but we'll write units on there. So notice 7, 17.5, and 27 are all done for you. You never have to actually physically do quartiles by hand. Is that okay? All right. So the next thing is the interquartile range. Root word inter means inside, right? So it's this idea of this range, but inside, all right? So what we're going to do, it's right here. I don't know if you highlight or circle things, guys. Your interquartile range is taking your highest quartile, Q3, minus your lower quartile, Q1, to get the middle 50%. This is the middle 50%. Because what we've done is this is kind of a good visual. What we've done is we change it into quarters. Here, 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 and here. So if I do this span, it's the middle 50%. And again, it's resistant, right? If I said, oh crap, guys, I didn't mean for it to be a 34, I meant for it to be 44, or 84, or 94, that doesn't really change, well, that really changes my range, but it wouldn't really change my interquartile range. So it's kind of like the median of spread, all right? So how's the IQ, let's figure out what the IQR is first of all. So the IQR for this problem above is Q3 minus Q1, which will just be 27 minus 7 or 20. And the question is, how is it interpreted? It's interpreted similar to range. to range and standard deviation. The larger equals more spread of data. The smaller, more compact data. Another thing I want to note, guys, use this to measure spread when data is skewed. And I'll talk about that at the end, okay? Remember, skewness just means there's a really, really high value or a really, really low value pulling it one way or the other, which standard deviation would be affected and range would be really affected. But your interquartile range isn't. It's resistant, okay? So if you have skewed data, you want to use the median to measure the middle and the IQR to measure the spread. And I have a place somewhere where we kind of write all that at one point. A lot of times, though, we don't use IQR by itself. We use it to help identify outliers. And outliers are exactly what it means. They're outlying the rest of the data, okay? So say, I can't use your guys' class very well because you were awesome at attendance, but say you guys have some other classes where there's like one student that consistently misses already, okay? So say this, first exam's coming up and that one student hasn't been there, but all of a sudden they show up for that test. Do you think it's fair to use that one student's test in the average to say how you guys did as a class? Not really, okay? If someone's not been there and they don't do that well, you don't want that to affect the rest of the data. So what's nice is what we do is we identify outliers, and a lot of times we can just throw that stuff out and say, okay, the outlier exists, but we threw it out. We didn't make it part of our actual data. So let's go ahead and look at the top of page 8. This is how we check for outliers, guys. On the exam, they will have these formulas, okay? So again, you don't have to memorize them, you just have to be able to use them. So the first thing we're going to do is determine the first and third quartiles. I would just do that on my calculator. Compute the interquartile range. Remember, that's IQR equals Q3 minus Q1. That's just from the bottom of the last page. Then what we're going to do is we're going to use the IQR in the calculation to come up with fences. Fences are exactly what you think. A fence keeps things inside, right? So if our data lies within our two fences, it's not an outlier. But if it's on the outside of our fences, we're going to say it's an outlier. So we're going to find this lower bound and this upper bound. And as long as all of our data lies within those two numbers, we're good to go. So it says if a data value is less than the lower fence or greater than the upper fence, aka outside of the fences, they're called outliers. So what I have here, guys, is the exact same data set, but I changed the 34 to a 54. So the question is, now that that's a 54 and a 34, is he far enough out to say, ooh, we got to, like maybe these are, again, ages, I don't know of what, but that 54 is a little too old, we got to throw that out. So in your and you don't have to do this, but in your list, everything exactly the same except for the very last value, 34, and I'm just going to type over it and write 54, okay? I'm going to go to stat and calculate, but what you're going to notice is it definitely changes my sample mean and my standard deviations, but what it doesn't change are my quartiles, right? That's what I talked to you about. It's resistant, so just changing that 54, it didn't do anything to my quartiles. So what's still my Q1? 7. What's still my Q3? 27. And why do I care? Because I can now figure out my IQR, which we already did, was 7, or 20, excuse me. All right, so we already knew all that. That data is the same data as the page before it. What I'm going to do is I'm going to find my lower fence. So my lower fence is LF equals, and I'm going to I'm going to write this generic formula. Q1 minus 1.5 times my IQR. Q1 minus 1.5 times your IQR. At that point, guys, it's just a puzzle. Here's your puzzle. You now have the pieces, right? What is your Q1? We found it. It was 7 minus 1.5 times your IQR. What was that? 20. You got it. Order of operations, just throw it in your calculator. It should multiply first and then subtract from 7. When you do that, guys, you get, it's pretty negative. Negative 23, does that look right? Okay, so it's pretty low. And all it's saying, guys, is all these small numbers, 1, 3, 4, 7, 8, are easily inside our lower fence. As long as we're greater than negative 23, we're good. If for some reason we have negative 50 in our data value, that would be an outlier, okay? But we weren't worried about these numbers. We're kind of worried about this 54. So let's go ahead and calculate our upper fence. Our upper fence is calculated very similarly, except for our jumping off point is now Q3, okay? And we're going to add 1.5 times our IQR, okay? So I'm just stealing this formula from right above, Q3 plus 1.5 times your IQR. We know what our Q3 was. It was 27 plus 1.5 times our IQR of 20. Beeper bopper beep, you put it in your calculator, do you guys get 57 there? Does that look right? Does anybody have a question on why the numbers are where they are? Okay. Remember, the lower and upper fences, those formulas will be given to you. You just need to know what Q1 and Q3 mean and what IQR means. But guess what else is on your formula sheet? IQR. I mean, it all just kind of comes down to itself. So, we have the lower fence of negative 23. We have the upper fence of 57. What do we know about all our data points compared to those two numbers?
None of them are outliers.
They all fall in that, right? I mean, physically think of a fence, right? 57 would be like around here. Negative 23 would be way down here, right? All of our data lies within those boundaries. So what does that mean as far as an outlier goes? We don't have one, okay? No outlier. And I don't know if you want to like maybe make a note of it. All data values lie within fences or something.